Welcome to our latest video on the topic of energetics. This is all about energy changes during chemical reactions and is suitable for GCSE students. By the end of this video lesson, you should be able to explain the differences between endothermic and exothermic reactions in terms of temperature change and energy transfer to or from the surroundings. You should also be able to draw energy profile diagrams for endothermic and exothermic reactions, and be able to use bond energy data to calculate overall energy changes for a reaction and to identify whether the reaction is endothermic or exothermic. So let's start by explaining what we mean by exothermic reactions and endothermic reactions. An exothermic reaction is a reaction that gives out heat. In energetics, we use the term system and surroundings. The system is the chemicals that are actually reacting, and the surroundings is everything else. So the test tube that the chemicals are placed in, or the beaker that the chemicals are placed in, or the air surrounding the beaker, or your hand holding the test tube, that's what we mean by the surroundings. In an exothermic reaction, energy is given out from the system to the surroundings. And we know a reaction is exothermic if there is a temperature rise. Because when we're measuring the temperature in a chemical reaction, we're measuring the temperature of the surroundings. And if the surroundings have a higher temperature, it means heat has been given out from the system, and the reaction is exothermic. A way of remembering this is that you go out through an exit. So therefore, exothermic means to give out energy. Examples of exothermic reactions include combustion reactions, where you burn a fuel in oxygen to release energy, or neutralization reactions, where an acid and an alkali react together and cancel each other out. These both lead to temperature rises and are exothermic reactions. Now, in endothermic reactions, heat is taken in from the surroundings, and it's the system that takes in this heat energy. The chemicals take in the heat energy from the surroundings. Now, if the surroundings have lost heat energy, it will result in a temperature drop. Examples of endothermic reactions include ammonium chloride and water. When you put ammonium chloride in water, the temperature decreases. This is because the chemicals, the ammonium chloride in the water, take in heat energy from the surroundings. That's why the temperature decreases. So the key thing you have to remember in this topic is exothermic reactions give out heat, endothermic reactions take in heat. Exothermic reactions cause a temperature rise because the system, the chemicals, have given out heat energy to the surroundings. You measure the temperature of the surroundings, the temperature goes up because it's an exothermic reaction. In an endothermic reaction, heat has been taken in by the chemicals, by the system. The surroundings now have less energy, therefore you notice this by a temperature drop. Energy profile diagrams allow us to see the energy changes that take place during exothermic reactions and endothermic reactions. And the following diagram shows the energy changes that take place during an exothermic reaction. So if we plotted the energy that we start with, the reactants, the chemicals at the start, and plotted what happens during the course of reaction, you would get a diagram such as this. Because what happens is the reactants have to have a certain amount of energy for a reaction to start. That's called the activation energy. And you will see on the diagram that's represented by this peak. And once that activation energy has been met, you end up forming products. Now, in an exothermic reaction, the products have less energy than the reactants. So therefore, energy has been lost to the surroundings. That energy drop from reactants to products results in energy being given out to the surroundings. And when we measure the temperature of the surroundings, we measure a temperature rise. So you've got to remember that in an exothermic energy profile diagram, the products have less energy than the reactants because heat has been given out to the surroundings. Now what we want you to do now is pause the video and see if you could draw an energy profile diagram for an endothermic reaction, a reaction which takes in heat from the surroundings. So pause the video and have a go at drawing what you think the energy profile diagram would look like for an endothermic reaction. So let's see how you got on. So here's an energy profile diagram for an endothermic reaction. So when plotting the energy changes that take place, you still have to include the activation energy, but this time the products have more energy than the reactants. This is because energy has been taken in from the surroundings. So the system, the chemicals, take in energy during the course of the reaction, and therefore that's why you have a diagram where the products now have more energy than the reactants. In an endothermic reaction, remember, there is a temperature drop because you're measuring the temperature of the surroundings. So the surroundings now have less heat energy because this heat energy has gone to the system, the chemicals. They've taken in the heat. So endothermic and exothermic reactions have a number of uses. So an endothermic reaction could be used in a cold pad for treating a sprain injury. So in one of these pads you would click a little button in the pad and two chemicals would mix. You get an endothermic reaction, the pad becomes really cold, and that could be used to treat an injury. You can also have this sort of technology in hand warmers where once again two chemicals mix. It's an exothermic reaction, it gives out heat. Exothermic reactions are also used in products such as self-heating cans and self-heating food packaging. These products very often work by having chemicals such as calcium oxide in the walls of the packaging. Alongside the calcium oxide, you will also have water in the walls of the packaging. And therefore, if you press on the bottom of the can, you will release the calcium oxide into the water. This causes an exothermic reaction and you will find that the food heats up. Now the calcium oxide is kept separate from the food because it's in almost like a secret compartment in the can or in the packaging. So this exothermic reaction allows you to heat up the food without something like a hot plate. In the next part of the video, we're going to look at how we calculate the overall energy change that takes place during a chemical reaction. And we're going to show you how we do this using what we call bond energy data. Now, when we're talking about an energy change in a chemical reaction, we're talking about the heat energy change that takes place. And that's represented by delta H, the change in heat energy. Delta means change and the H represents the heat energy. So we're measuring delta H, the change in heat energy during a chemical reaction. Now to work out the overall energy change for a reaction, we have to calculate first the bond breaking energy. That is, how much energy is required to break all the bonds in the reactant molecules. We also have to calculate how much energy is given out when we form the products. And the overall energy change is bond breaking energy minus bond forming energy. So we're going to take you through some example calculations and then we're going to give you some practice questions to do. So let's look at example question 1. So in this question we have hydrogen reacted with chlorine to form two HCl molecules, and I've drawn out hydrogen, chlorine and hydrogen chloride in a form that allows me to see all the bonds present. Now the table shows you the bond energy data, and it shows that a HH single bond requires 436 kilojoules to break it. A Cl-Cl single bond requires 242 kilojoules to break it, and a HCl bond requires 431. Now that's the energy to break the bond, but when we form any of those bonds, we get the same energy given out. So what we mean by that is breaking a HH single bond requires 436 kilojoules. But if I formed one of these bonds, 436 kilojoules would be released. Now, the aim of this question is to calculate the total energy change that takes place during the reaction. So, to help us do this, the question is broken down into several steps. Part A asks us to calculate the total energy needed to break all the bonds of the reactants. Part B asks us to calculate the total energy released in forming all the bonds of the products. And if we know the bond breaking energy, part A, and the bond forming energy, part B, we can use delta H equals bond breaking minus bond forming to work out the total energy change for this reaction. And that's what we're going to do now. Let's look at how we go about answering this question. So, first thing we do is work out the total energy required to break all the bonds in the reactants. So, the reactants are made up of hydrogen and chlorine. There's one HH single bond and one Cl-Cl single bond. So what I do is work out the energy required to break both of those. So it will be 436 added to 242. And that gives me a bond breaking energy of 678 kilojoules. Now in the question, they put the units as kilojoules. It's more correct really to put this as kilojoules per mole. And that's what you'll see more commonly in questions. So I put it as kilojoules per mole here. Now the bond forming energy is the total energy that we have on forming the bonds. Now remember, a HCl bond releases 431 kilojoules and we have two of them. So the bond forming energy is 862 kilojoules per mole. So to work out the overall heat energy change, delta H, we do bond breaking energy, 678, minus bond forming energy, 862. And that gives me an overall energy change, delta H, of minus 184 kilojoules per mole. So when you get a negative value for delta H, it means you have an exothermic reaction. Delta H is negative here because more energy is released on forming bonds in the products than was used to break the bonds in the reactants. Because the bond forming energy is higher in terms of its value than the bond breaking energy, you have an exothermic reaction. So that's what we've got to look out for. If you get a negative delta H, it means that it's exothermic, and it means more energy is released on forming the bonds than was needed to break the bonds of the reactants. So now let's look at example 2. In example 2 we have methane reacting with two oxygens to form carbon dioxide and two water molecules. And once again we've drawn out the molecules so we can see all the bonds that are present in the reactants and products. The table shows the energy required to break the bonds, and remember the same energy is given out on forming the bonds. And the question has the same format. It's asking you to calculate the total energy needed to break all the bonds of the reactants. Then it's asking you to calculate the total energy released in forming all the bonds of the products, and then to calculate the total energy change for this reaction. So we work out the bond breaking energy, we work out the bond forming energy, and then bond breaking minus bond forming gives me the overall energy change for this reaction. So let's go about how we would answer this question. So first of all, we do part A, which is work out the bond breaking energy. To do this, I look at the diagram which shows me all the bonds that are present. Now I've got 4 CH bonds in methane. So the energy required to break all the bonds in methane is 4 times 413. 413, remember, is the energy to break a CH bond. So I've got 4 CH bonds, so the total energy is 1652. And then I've got 2 oxygen double bonds, and each double bond oxygen is 497 kilojoules to break it, so 2 of them would be 994. Add them together and I get a total bond breaking energy of 2646 kilojoules per mole. So in part B, I have to work out the bond forming energy. So I've got carbon dioxide, which is made up of two CO double bonds, and each of these releases 805 kilojoules. So therefore, if I've got two of them, it releases 1610 kilojoules per mole. I've got two water molecules. Now a water molecule is made up of two OHs, and I've got two of them. So four OHs would release 4 times 463, which would be 1852 kilojoules per mole. Add this up, and I've got 3462 kilojoules per mole. To work out part C, the overall energy change for the reaction, delta H, I do bond breaking energy minus bond forming energy. So we have 2646 bond breaking energy minus 3462, which is the bond forming energy, and that gives me minus 816 kilojoules per mole as the energy change in this reaction. Now the question is asking me, is it endothermic or exothermic? It's exothermic. This is because it's a negative delta H, and the reason it's exothermic is because more energy was released on forming the bonds than was used to break the bonds of the reactant molecules. So I have 3462 is a bigger number than 2646. That's why the overall energy change is negative and it's exothermic. So now it's your turn to have a go at some practice questions. So we want you to pause the video, have a go at the questions that follow, and then we'll go through the solutions one by one. Here's question 1. It involves the Haber process. Nitrogen, N2, reacting with 3 hydrogen molecules to form 2 ammonia molecules, NH3. And we want you to use the bond energy data to calculate the total energy needed to break all the bonds, and then the energy released in forming the bonds of the products, and then the total energy change. And from this, we want you to say if the reaction is endothermic or exothermic. So pause the video, have a go at the question. So here's the solution to question 1. The bond breaking energy is 945. That's the energy required to break a triple bond nitrogen, added to 1308, which is 3 lots of 436, because remember 436 was the energy required to break a HH bond, and you've got 3 of them, so that's why it's 1308. Add them together, it's 2253 kilojoules per mole. The bond forming energy is 6 lots of 391, because there are 6 NH bonds. Remember, there are 2 ammonia molecules with 3 NH bonds in an ammonia molecule. You've got 2 ammonia molecules, so therefore there are 6 NHs, which is 6 times 391. That gives us a bond forming energy of 2346 kilojoules per mole. So to work out delta H, we do bond breaking minus bond forming. So we do 2253 minus 2346. That gives us a delta H of minus 93 kilojoules per mole. As delta H is negative, that means that the reaction is exothermic, and it's exothermic because more energy was released on forming the bonds of the products than was used to break the bonds of the reactants. So here's question 2. It involves 1 molecule of ethanol reacting with 3 molecules of oxygen to form 2 molecules of carbon dioxide and 3 molecules of water. The bond energy data is shown in the table, and we want you once again to calculate the total energy needed to break all the bonds of the reactants, then to calculate the total energy released in forming all the bonds of the products, and then finally to use this to work out the total energy change for the reaction and to determine whether it's exothermic or endothermic. Pause the video and have a go at the question. Now let's go through how we answer this question. So we work out the bond breaking energy, part A, and to do this we have to work out how many bonds are in the reactants, and we have to break them all, and how much energy is required to break them. So there is 1 CC bond, so that's 346. There are 5 CH bonds, so that's 5 times 413, which is 2065. There is a CO single bond, and that is 360. And then there's an OH bond, and that's 463. And there's 3 double bond oxygens, so that's 3 times 497, which is 1491. Add them all up, gives you a value of 4,725 kilojoules per mole for the bond breaking energy. Now we move on to part B, working out the bond forming energy, the energy released on forming the products. So we have 2 CO2 molecules and 3 water molecules. Each CO2 molecule has 2 C double bond O's in it, and if we have 2 molecules, we have 4 of them. So that's why it's 4 times 805, which is 3,220 kilojoules per mole. And then we have 3 water molecules, and there are 2 OHs in each water molecule. So there are 6 OHs. 6 times 463 is 2778 kilojoules per mole. Add them up, and we have bond forming energy, which comes to 5998 kilojoules per mole. Now to work out delta H, we do bond breaking minus bond forming, so it's 4725 minus 5998. This comes to minus 1273 kilojoules per mole. The minus tells us that it's exothermic, and it's exothermic because more energy is released on forming the bonds of the products than was needed to break the bonds of the reactants. So here's question 3. Question 3 says hot cans are designed to heat the food inside them when it is to be eaten. The heat is generated by mixing calcium oxide with water. The following diagram shows the cross section of a hot can. During a trial reaction, the temperature reached 50 degrees C, but a temperature 70 degrees C is required to properly heat the food. Suggest a change that could have been made and explain how this would lead to the can reaching the higher temperature. So have a go at this question. It's worth 2 marks. Pause the video, have a go at the question, and then we'll go through the answer. So for this question, there's 1 mark for a sensible suggestion and 1 mark for an explanation to this. So the examiner would accept using more calcium oxide, so more heat would be released during the reaction, or using smaller pieces of calcium oxide, so the reaction occurs more quickly due to the higher surface area. So here's part B. When chemical reactions take place, bonds are broken and new bonds are formed. The question is asking you to explain in terms of bond making and breaking why some reactions are exothermic, and there's 2 marks for this. Pause the video and have a go at the question. So when answering this question, if you explain that bond breaking takes in energy and bond forming releases energy, you get a mark for that. And if you explain that reactions are exothermic because more energy is released on forming the bonds than was used to break the bonds, than was absorbed or taken in to break the bonds of the reactants, you get a mark for that. And you can get both marks by a single statement. If you said reactions are exothermic if more energy is released in forming the bonds than was absorbed in breaking the bonds, you would get both marks for that. To conclude this video, let's look back at our lesson objectives. So after watching this video, you should now be able to explain the difference between endothermic and exothermic reactions in terms of their temperature changes and energy transfer to or from the surroundings. You should also be able to draw energy profile diagrams for endothermic and exothermic reactions and be able to use bond energy data to calculate overall energy change for a reaction and to identify whether it's exothermic or endothermic from this energy change. So that concludes our video. Please check out our YouTube channel, Dr. O Chemistry, and our Twitter site, which contains lots of chemistry information and links, @RadaChemistry.